Right, this video is on finding transformations and the different characteristics of quadratic functions. So first, we're going to go ahead and write in this little space just a basic table for y equals x squared. So we're going to plug in x values from -2 to +2. So -2 squared is +4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and then 2 squared is 2. And so for us to be able to graph this by hand without a calculator, we're going to go ahead and use those transformations on these points. So the transformations that we have are a vertical stretch of 2. It is shifted to the right 2 and up 3. So the transformations work exactly the same as what we've studied in the past. The inside of the function still moves left and right. The end of the function, or the outside, any number that's added or subtracted on the outside, moves it up and down. A number multiplied in the front is going to stretch or compress based on the size of the number. And then if it's negative, it's going to reflect over the x-axis. So we found the transformations. We can go ahead and find the vertex. It's the opposite of that number and then exactly the same as that number on the end. And so that means that the vertex is +2, +3. And so now I'm going to go ahead and make a chart with all those points so that I can graph. 2 squared is not 2, it's 4. Goodness. So that I can go ahead and graph the equation without using my calculator. Okay, so to stretch a function by 2, it means you're making it twice as tall, so the y coordinate is going to double. And then to shift to the right 2, right, we're going to shift to the right 2. So I'm going to add 2 to the x coordinate. And then I want to shift up 3. So I'm going to add 3 to the y coordinate. And then the points in the column at the end are the points that we graph. So we've got 0, 11, 1, 5, 2, 3, 3, 5, 4, 11. So make sure I got my arrows. All right, so the pattern with quadratic functions, with a normal quadratic function, is it goes over 1 up 1, and then over 1 up 3, and then over 1 up 5, and then over 1 up 7. So it goes up the odd numbers. So if this graph has been stretched, then instead of going over 1 up 1, over 1 up 3, over 1 up 5, it's going to go up 2, up 6, up 10. So the amount that it goes up doubles each time. So that's, I'm telling those of you who like to kind of do this without making the table, that's how you could kind of do it without making the table, is to understand how it grows. Okay, so we have that one graphed. Let's go ahead and try the next one. So again, we're going to find the transformations. It has been reflected over the x-axis. Shifted to the left 4 and down 5. And again, I'm going to go ahead and take the beginning points so that I can make a table. It is hard for me to talk and use my brain at the same time. Oh, goodness. All right, and I didn't write the vertex, but we can find it. -4, -5. Okay, so each point has been reflected over the x-axis, so that means that all of our y-coordinates are going to turn negative, because you're taking a graph that goes up, and you're going to make it go down instead. So that's taking the y-coordinates and making them all negative. And then from there, we're going to move all the points left 4. And we're going to take all the points and move them down 5. So we have the point -6, -9, -5, -6, -4, -5, -3, -6, -2, -9. And this problem, this quadratic that we're graphing, is actually an inequality. And so that means this symbol means I'm doing a solid line, but I also need to figure out how I'm going to shade this. So there's my solid line. And I'll go ahead and I'll plug in 0. So I've got 0 is less than or equal to the negative version of 0 plus 4 squared minus 5. So I have 0 is less than or equal to 0 plus 4 is 4. So I have the negative version of 4 squared, which is 16. So 0 is less than or equal to -21, and that is false. 0 is not less than a negative number. And so since 0 is outside the parabola, that means that inside the parabola is what gets shaded. So there's our shading right in there. All right. Example 3. So we're going to find the vertex, the transformations, the domain and range. So here's our characteristics question, and we have a lot of characteristics to find. So our vertex is -1, -7. The transformations, the graph has been compressed by 1/2. It has shifted left 1 and down 7. The domain of a quadratic is always going to be -infinity to +infinity. If you think about what a quadratic is asking you to do, it's asking you to square a number or multiply a number by itself. There's no number that I could pick where you couldn't multiply it by itself. Any decimal that I pick, you can always multiply those by themselves. I can take pi and multiply it by itself. I can take a square root and multiply it by itself. I can take a negative and multiply it by itself. So the domain is -infinity to +infinity. You can also tell that by looking at a graph, because these go left forever and they go right forever and there's nothing missing in between. So -infinity to +infinity is going to be the domain. The range, it would be helpful to have like a little sketch of the graph. So what I do here, and my sketch is not perfect, it really is just like, does it go up or does it go down? And then I typically label the vertex. So my sketch is going to be like that, a U-shaped graph that goes up and has a vertex at -1, -7. So if we're thinking about the range, then the part of the vertex we're going to use is the y-coordinate, and we're going to say the furthest down the graph goes is -7. The furthest up the graph goes is +infinity. So I'm going to say the range is from -7 to infinity. Parenthesis around infinity because I can't actually see that number when I graph it, but -7 gets a bracket because that number really is showing up right there. All right, increasing and decreasing intervals. I like to do a separate picture for this because I like to label my picture. So if we have a little stick figure, he starts up here, he is decreasing, it's like he's walking down into a valley until he hits this value, and then he goes up and he starts increasing on the other side. And so this x value that he hits is -1. The x value of a right arrow is positive infinity. The x value of a left arrow is negative infinity. So the decreasing interval is from negative infinity to -1. And the increasing interval is from -1 to infinity. Okay. We're going to find the max and min. So a maximum is when the graph has a high point. So for example, this equation or this inequality has a maximum. It does not have a minimum because it just goes down forever. Minimum would be a low point. So this graph has a minimum, but it doesn't have a maximum. And you'll notice that the vertex is always that point. So for this one, we're going to have only a minimum at -1, -7. We do not have a maximum because the graph goes up forever. So I'm going to say none. There's no specific high point on the graph, right? And then we're going to look for the intercepts. So I'm going to find x-intercepts and y-intercepts. I'm going to go ahead and graph this. Just going to clear my calculator real quick. So I've got 1/2 x plus 1 squared minus 7. It's not that I can't do this by hand, it's that when we get to Math 3, we want to be more efficient and do things quickly, and that means often doing it in a calculator. So to find the x-intercepts, I'm going to do second trace, option number 2, and my calculator is going to ask me to do left bound and right bound. So my first intercept is right here, so I'm going to hold the cursor until it gets to the left of my pencil. So there's my left bound. I'll press enter, and then I'm going to hold the cursor until it gets to the right of my pencil. There's my right bound. Ignore the guess. So there's my first x-intercept, which is -4.742 if I round it correctly. And then my second x-intercept is over here. There's my second x-intercept, and so that's a good left bound. And then my right bound would be over there. And so that x-intercept is 2.742. And to get my y-intercept, I'm going to do second trace, option number 1. And to find the y-intercept, we always plug in 0. So the y-intercept is 0, -6.5. Okay. Next, they're asking if the parabola is continuous. So, and it could be an upside down parabola or a right side up parabola. So remember that word continuous means you can trace the graph or you could say you could trace the line or you could trace the curve. You can trace the graph without picking up your finger. So it means the graph doesn't jump at all. There's not like spaces in between it. It just is one, like continuous line. So if we think about these parabolas, I can start at the arrow and trace it. I can start at the arrow and trace it. I can start at the arrow and trace it. And so the answer is yes. If anyone ever asks you about the continuity of a parabola, you just always say it's continuous. The whole thing is continuous. All right, what is the end behavior of a parabola? Sorry, I stopped moving, so my lights turned off. The end behavior of a parabola is describing in mathematical notation what the arrows are doing. So I've got two options. I've got a parabola that goes up, and then I'll put it over here. I've got a parabola that goes down. Right, so here's how we think of it, because we have different ways of thinking of infinity. We can think of infinity as you go to the left and right forever. So as you go to the left forever, we would call that negative infinity. As we go to the right forever, we would call that positive infinity. But we also have up and down. So as we go up, that would be positive infinity. As we go down forever, that would be negative infinity. So end behavior is saying as you go to the left forever, are you going up or are you going down? And as you go to the right forever, are you going up or are you going down? So we're going to say as x goes to negative infinity, which means as x goes to the left forever. And we're also going to do as x goes to positive infinity, as x goes to the right forever. So for this picture, as x goes to the left forever, that's the left side, the arrow goes up. So that means that y goes to positive infinity. As x goes to the right forever, y goes up. So y goes to positive infinity. We're going to do the same thing for an upside down parabola. So as x goes to the left forever, and as x goes to the right forever, and in both of these, the arrow goes down. So I'm going to say the y-coordinate goes to negative infinity. So you could say, oh, both arrows go up. And that is kind of like the common sense way of saying this. But to answer these problems, now that we're in a more advanced math class, we're going to go ahead and use this math notation to describe the end behavior.